All right. Hello, everyone. How are you enjoying NDC Porto so far? Yeah. Good. So my name is Dennis. I'm a manager at Phoenix Contact. Don't worry, I'm a manager now. I used to be a software engineer, and thank you, Jody. And I'm actually leading a software development team in the Industrial Cabinets Solutions business unit at Phoenix Contact. And welcome to my talk, Introduction to Unsafe C#, or alternatively, and more accurately, calling native code and crashing in entirely new ways. You won't believe how you'll be able to crash when I'm done with you. To crash and burn. But before we go into this, and we got a lot to cover, the talk focuses very, very much on the what and the how to do it, but I talk only a little bit about the why, because the what and the how, that already takes a lot of time. So really, there are three main scenarios I can think of why this will be useful. One, in your quest to avoid not invented here syndrome, I hope you try to avoid that, you'll find a library out there that does exactly what you need to do, but it's native and there is no managed wrapper. Now, for anything that's popular, this is kind of unlikely at this point. .NET has been around for a long time, but this might happen if it's more niche or maybe something developed internally. Secondly, in your quest to avoid not invented here syndrome, you find a library that does exactly what it needed to do. There is a managed wrapper, it's stable, it's great, but the wrapper doesn't work the way you need it to work. And the SQLite example I have in the talk, it's a real-world example that falls in that category. And third, I just want to mention it, totally out of scope here, you're starting a brand new greenfield project, and you want to do something that is not fast enough or impossible to do in managed code, and you need to create a mixed native and managed solution. So that's what this is really all about. So what we're going to cover is, first, we need to understand what is unsafe code in the first place. That's an introduction, so we should probably explain what that actually means. What unsafe C# features are there, because once we opt into unsafe code, there's a whole new language features that are now all of a sudden available to us. Memory layout is going to be interesting. It's one of these things you had not to worry about until you hit this strange new world of unsafe C#. And then platform invoke, this is where it gets interesting in a sense. This is why you need all the stuff I talk about until this point. This is what we actually want to need. This is this calling native code and crashing in cool ways. And then when we have unmanaged resources, we need to manage them somehow. So we talk about the management of resources, the lifetime. Callbacks, that is something we will probably encounter at one point or another in native code. And then there's a couple more pointers and hints, pointers, no pun intended, about what else you should probably know. So, what is unsafe code? And I start this with this little example here. Now, consider this. There is a string, and we're initializing this with hello world. So far, so good. And then this piece of code says, OK, now we're calling an extension method on that string called ASCII to upper. And then I print this to the console. And the comment here claims, at that point, all of a sudden, this string is now all uppercase. Who here thinks this is actually possible? OK, a few. So I guess everybody who didn't raise their hand probably thinks that, but strings are immutable. And immutable means I create them, I can't change them. I change them by creating a new one with whatever change I want. So yes, this is possible. And yes, this is a very bad idea, because everybody assumes that your strings are immutable. So if you start now mutating immutable strings, you're asking for trouble. Maybe there is some niche scenario where it's a new string, nobody else has a reference to it, and you want to do something like this. But generally, just don't. The reason I'm starting with this anyway is simply, you can forget most of what you hear today. You may remember some terms, and you know my presentation and what you look up in the documentation. But this you need to remember. Unsafe code is to be taken very literally. It means the type and memory safety guarantees you are very used to and very attached to, they go out of the window. There's just memory, and we can do whatever we want with it. Now, what does the specification say? It kind of says the same thing, but in more elaborate, nicer terms. So it talks about that we now can declare and operate on pointers, and we can convert pointers to ints and so forth. The last sentence of this little paragraph is interesting, though. It says, in a sense, writing unsafe code is much like writing C code within a C# program. And that is true in two ways. One is this, you now have pointers, you have memory, you can do whatever you want with this memory, but also syntactically, if you've dabbled in C a little bit before, then you'll recognize most of the syntax, and of course all the problems I'm going to talk about that unsafe code has. So, going to the crashing part. It's my favorite part. So unsafe code means new kinds of bugs. So for once, now we can have buffer overflow. You know, these things that we see vulnerabilities because there's a buffer overflow, and then we can inject code. Guess what? We can have this in our .NET application too. It's great. We don't need C or C++. We can do this ourselves. So I have a pointer to some buffer, and I can read past the limit of this buffer, or I can write, even worse. If I'm lucky, I get an access violation. And I say, this is really the good case, because now you know there's a problem. It crashed. Well, you can debug and see what you're doing wrong with your pointers, because it might actually run. It might run for a long time. There might be difference in behavior between debug and retail builds. And going back, right, there is sometimes literally decade-old vulnerabilities in, what was the case, Bash, I think, for example. This might actually go unnoticed for a long time and be exploitable. Speaking of exploits, there is stack and heap corruption. So yeah, reading is bad enough, but if I'm writing and writing past a buffer boundary, then I'm going to overwrite something that's there. Maybe it's not in use. This time you run the application, but maybe you will overwrite something important. Yeah? Okay. So that's a It's very unsafe, yes. I don't feel safe at all right now. So are we back? Okay. Yeah, this new bug, see? Even this is affected somehow. I can't explain that, so you have to ask the AV crew. So yeah, we can corrupt stuff. We might introduce vulnerabilities. We can have dangling pointers. This is a classic in C, C++ land, but good news, we have two variations of this. So the classic is the use after free. I have a pointer to an object, it's all good. I free this object, but I still have this pointer, and I still dereference it. So bad things can happen. It's an undefined state. Maybe I'll just read some old data. Maybe somebody else has written already there and read garbage. Again, if you're lucky, you get an access violation because the page is gone. But since we're .NET, for us it's even worse. There can also be use after relocation. So the garbage collector, if you remember, does two things. It collects garbage, as in, okay, these objects are not reachable, we're going to free them. But it also compacts the heap. It moves objects around in memory. So what can happen, I can get a pointer to a field of an object, and that object could move around after I got this pointer. And then I dereference it, and again, who knows what I got? And memory leaks, and I like to call this true memory leaks. So yes, you can leak memory in .NET in that typically you have references that you didn't mean to keep, but you keep them anyway, and delegates are a nice way to do this, right? Some event handlers that you need to clean up, but you forget, they accumulate. But oftentimes they're somewhat easy then to spot. You know you have a leak, you create a memory dump, you look at the heap, and okay, these are all these objects I didn't expect. You can see where they're coming from. Here, this means I have unmanaged heap allocations, and at some point, I have an allocation for which I don't have a pointer anymore at all. There is no way to free this short of restarting my process. And there's also tools to then debug this and analyze it, but while your process is running, really there's nothing you can do about leaked memory. You have to exit the process to free it. All right. So, unsafe C# features. Let's break down this example I started with. Again, please don't do that. It's a bad idea. It's a very, very bad idea. But yeah, it's a great starter. So first of all, the declaration of this method, it says it's unsafe. So we're telling the compiler that we want to do something with pointers, with memory addresses. Other than that, it's just a normal extension method, nothing too fancy. But then the first line of the body has a fixed char pointer p equals s. So got a pointer already, and what this does, it pins this string s and gets the address. Now pinning, this is a mechanism in the GC where I can say, please do not move this object. That's an option I have. This would actually also then, or not would, this does then prevent the dangling pointer because an object was relocated. The problem is I should not do this for too long for any object because obviously this is not then subject to compaction, right? It stays there. The GC can compact around this, but it can't move whatever I pinned. So we do this as short as possible. But I have to do this when I would get the address, for example, here of the first element of my string. So once I got this, I iterate over my string, which really is a character array. And then for each element here, I got this little if statement where I look at the current element, so pi, I got pointer element access, which looks a lot like an array access because this is where the C comes in again, C, pointer, and arrays. There's a very blurry line between those two. So it's basically indexed access. I look at is this in a certain value range, and if yes, so it's the read, then I write to it, I change it from lower to uppercase. And this is opt-in not only in the code that I have to use the unsafe keyword, also I have to say to the compiler that I really, really want to do this. So if you use the default build targets, for example, this is not set, you'd have to set it in your project settings, or you can also set this as a flag if you invoke CSC directly, and if you're not, you get this nice CS0227 says, okay, it has unsafe code in it, but you didn't tell me that that's okay. It's actually compiled in error. So what else can we do with addresses? So there's a whole bunch of things I can get addresses of. You already saw one example. There's another one where I have a managed byte array, and again I can say fixed. I want to pin this array and then say byte pointer equals managed byte array. That gives me the address of the first element. What's interesting, in the first line, you don't need to use any operator in this case. You just give the name of the array. Again, goes back to how arrays/pointers are handled in C. Then the second example, I want to get a pointer to a field of an object. In this case, again, I pin it, I say fixed, and I say int pointer equals address of underscore integer. Now I have an address of this field. And fixed, that is also a scope, but if I now copy this address out and keep it and pass where my fixed ends, then I might have one of these dangling pointers. Going back to that. I can get the address, for example, of an argument or local. They're kind of similar anyway. So I get my address of double parameter, address of character. And then, of course, I can dereference them. The pointer is an address, right? Some address in memory, and I can say asterisk, double pointer, I dereference it, God damn it. And that gives me the value at that address. Structs are a bit special in that I can also get addresses of structs. And in this case, there is the dereference pointer and access member, which is just a shortcut. I don't have to dereference the struct pointer first and then access the element. I can do this in one operation with minus greater than. And again, I can set elements, I can read them. And finally, dealing with pointers, and this is very important, I've rewritten ASCII to upper in this way, which is longer and harder to read. This is just to illustrate pointer arithmetic, basically. So in the first one, I had a for loop. And here I say, OK, again, I need to pin my string and get the address of the first character in there. But then first, I do a copy. I say char pointer equals p. The reason I do this, P here is one of the very rare cases. I'm not sure it's the only one, but it's definitely a very rare case where you have a local in C# that's actually read-only. You cannot change P. So if you want to do anything with that, you have to copy it first. So this is my inclusive start address of the string I want to do something with. And then I calculate the exclusive end address. So I say char pointer end equals pointer plus s.length. And this is pointer arithmetic. So this is adding an integer to a pointer. What does that mean? So it doesn't actually add those two numbers as is, as if they were both integer. It does consider the type. So let's say the string is 10 characters long. A character in .NET is 2 bytes long. So it's the number 10 times the size of the type. In this case, character, 2 bytes, so we're adding 20, the actual number 20 to this address. So pointer arithmetic always considers the type. So now I have my end address, and now I'm just doing a while loop, which also shows you pointer comparison. That's probably not too exciting. I mean, they are numbers in the end, so I can compare them. Is it the same? Is it larger than or less than? And then also more for the sake of completeness. In this case, I didn't use the element access here. I explicitly dereference and then say, is it in my value range? And if so, then change it from lower to uppercase. And then again, the last one here, the pointer increment works the same way. So it's my pointer plus 1, but meaning 1 times the size of that type. So in this case, 1 times 2. So adding to the address to get to the next item. Now, I showed you a whole bunch of examples of getting addresses of stuff, but in terms of actual rules, what can I get addresses of? So basically, you can get addresses of anything that is a value type, so your primitives, your longs, your doubles. That includes structs. Also, if they're generic, it's all good, as long as there's no object references in there. So this is where the compiler draws the line and sees, oh, there's an object reference in there. You can't get the address. Not allowed. So an arrays of value type are an exception because the array is a reference type. But you're getting the address of the first element. So what's in the array needs to be a value type following these rules. Then I can get the address of the array being the address of the first element. And then strings, we've seen this in the example, they're just a fancy character array anyway. So getting address of string is the same basically as getting the address of a character array. Then if you violate this and it's a new object and you want to get an address of this, then you get a nice compiler error here, CS0208 said you can't do this unless you're on C#11. So I had this talk all polished that you can't do this. I was used to not being able to do this for 20 years, and then Microsoft said, no, now we make it possible. Now, this comes with some restrictions though, so it is now possible in C#11, you get a warning though. So in a sense, the compiler still doesn't like you doing this, but you're allowed to now. But what does this mean? So in order to demonstrate this, and quite frankly, when there was new also just to try it out myself, I created my little example here. So I have a managed type. It has a single ushort field. I initialize it with beef because that joke has never been done before. So I knew up an instance of this. So I got managed, an object reference to an instance of managed type. So then I pin it, and I got some addresses here. I got the address of that one field. And then I'm getting, because I can now, I'm getting the address of that reference. And you have to keep this in mind. So references, conceptually, they're opaque handles. Right? They allow you to access an object, but how, you don't really worry about. Implementation-wise, it is actually a pointer. So that means if I get a pointer to an object reference, I have a pointer to a pointer. There's 2 levels of indirection here already. So this is pretty nasty, but it gets better. So I'm printing out all these addresses. I'm printing out the address of the reference, the address of what this points to, the actual object, the field address, and the offset, if any. And you'll find something like this. OK, the ref address, boring, it's something on the stack, great. Then we got the object on the heap, and we got the address of the single field here. And you see there's an offset of 8 on 64-bit. And those 2 statements combined probably also already make you think, yeah, this is probably a pointer of some sort. Yes, it is. It's the pointer to the method table. So for Invoke, it's completely useless. I should really try at some point if you can write to those addresses. Because if you can then destroy the method table pointer that this instance has. And if you then dereference this, you can destroy that table entirely, theoretically. I hope that's read-only. But the bigger point is here, the object address is not that useful for Invoke because as what am I now giving this out? You could say a void pointer, so a pointer that is actually not typed. It's usually not that useful because the first field is then pointing to my method table. So I kind of have to add these 8 bytes or 4 bytes on 32-bit. If anybody can think of a reason why you want to do this, and to be fair, as far as I know, there is a reason for some edge cases, maybe in the runtime. They didn't do this just for fun. But for what I'm talking about, you have some native library that you want to use, or maybe you have to create your own. It can be done now, but I don't think it's all that useful. But you should understand that it's a thing and how it works. So going back to the more useful C# language features, if you will. If it is small and the lifetime is limited, I can have fixed size buffers inside structs. And this is a common pattern you'll find in native APIs. That you have a struct there, it's input or output, and it has a bunch of primitive fields, ints and whatnot, and then maybe like a 128-byte buffer for a string or whatever. Often it's a string. The limitation here is the type of those fixed size buffers. In a struct, they can only be of primitives, so I can't have other structs in there. So it has to be your byte short, longs, float, doubles, bool. Okay. See, the other thing I can do is I can do a stack alloc, so that literally allocates memory on the stack. And here I'm again free to use any kind of value type that I want. Those structs are possible again, but that is also not suitable for all cases. So for one, it's on the stack, and it used to be, I think it's still the case, that the default stack size on Windows is 1 megabyte. So if you need a 2 megabyte buffer and you try to allocate this, yeah, well, you got a stack overflow. Not good. And of course, then maybe you wonder what's going on, and you stack overflows on stack overflows, and it's stack overflow inception. So size, but also lifetime, right? So it's on the stack. So as soon as whatever method performed the stack alloc returns, this is gone. Or if you keep a pointer, you got a dangling pointer. So we'll talk about what else you can do a bit later, but those are some things you can do for these buffers. But before we go to that, let's talk about memory layout. This is interesting because so far, if you're new to Unsafe C# and native code, you don't have to worry about this, right? You load assemblies, they're full of IL, and the runtime makes sure that everything just works. It's great, I like it. But of course, it's not true as soon as native code is involved. And one thing you need to know about is packing size. And that literally is one mechanism that plays into how fields are exactly put onto which offsets in memory. So I'm starting here with my default packing size, meaning I don't specify anything, which in C# is actually equivalent to me saying struct layout sequential pack size 0, meaning default of the platform. And in this case, I just have 2 bytes, and I have a long, and the oval size is 16. Why? Because the runtime likes to align fields on natural boundaries. So your character, your short, they're 2 byte. They're supposed to be aligned on 2 byte boundaries. Your ints and your onside ints, they're 4 bytes, so they're supposed to be aligned on 4 byte boundaries, and so on. So B1 starts at 0, then B2 follows at offset 1, but then long needs to be aligned on this 8 byte boundary, hence 16. Now what I can do now is I can say, okay, I want a different packing size, meaning I basically specify a different maximum, if you will. So again, the runtime will look at all the fields and their types. And for the bytes, it doesn't matter, but then for the long, it goes, okay, the long is 8 byte, but you told me packing size 4. 4 is smaller than 8, so I'm going to pick that. So in this case, I end up with 12. Now, first of all, obviously, this has to match between your structs and the native structs, otherwise things won't work. So as a general hint, you got your DLL imports and your structs, all the stuff we're still going to get to, defined in managed code, and you're sure the types match correctly, but it still won't work. This might be a reason why. And a reason also why you might mess with this, generally speaking, but especially on the native library side. So for your RAM, for running locally, it probably doesn't matter all this much, but what if you use your struct to send data over network or write it to disk? So in the first example, we have 6 bytes of padding. This is never going to be useful. It's waste. So if we send this over the network, or we write it to disk, we have these 6 bytes wasted every time. Probably not that much of a deal for once or twice, but what if I have 1 million of these things? So might actually want to do this for certain use cases. It gets better, though. This is not enough. So in C, there's a thing called a union. And I need to come up with a better name. So this is strictly speaking not a union, because in a union, all fields are at offset 0. They don't have to be all the same size, but they all start at the same address. But it's still a nice example to talk about explicit layout, and you can take this literally. So when I say explicit, I'm telling the runtime, I'm telling you for every single field what the offset is. And I actually then have to tell it what the offsets are. So if I omit one of those field offset attributes, I'm going to get compile time error because, well, compiler says, well, you said you're going to be explicit and not being explicit. Make up your mind. I don't know what to do here. And this is interesting in that it's also a harmless example. So I have a short value at 0. And then, assuming it's a little endian system, I got the low byte at 0 and the high byte at 1, which is the definition of short. And I can read and write them now independently if I choose to. And there might actually be use cases for that, maybe not this exact, or maybe this even exactly, but you have an int or long, you want to read certain bytes of it. This is a way to do it. And notice what's not there. There is no unsafe in here as a keyword. As far as the type system is concerned, this is perfectly fine. And how this is used in native code is it's a way to basically be able to return different types of data back to a caller, or into a caller, right? It goes both ways. It's certain arguments that might be an int or a long, depending on certain other arguments or some state. And of course, it should be then clear what the correct one is to actually use. Because I could do something like this. Can throw a pointer in here. And also, more generally speaking, one thing that allows me to do that is otherwise not possible in the net, I can have a, sorry, I should say in C#, is a reinterpret cast. Meaning, normally when you cast from a long to an int, from a long to a double, or the other way around, it retains the value as far as possible. So the value ranges are not the same, so you might lose precision, you might get an overflow, but that aside, right, it's keeping the actual value. Here, it's just keeping the bit array, what's in memory. It's just interpreting in different ways. So I say, OK, I create a new struct here. I say long 47. So I got 47 as encoded for a long in memory, but then I read it as a double. Again, reinterpret cast. The bits don't change at all. I just read them now as if I had written a double. And then it prints this. It's a slightly different number than the one I wrote. Slightly. And then, of course, if I now have interpret the same bit pattern as a pointer, yeah, good luck. So yeah, this is something that you'll find. It should be clear what to read and write depending on what call you're making, what state you're in, and hopefully it's documented, but this is important to get right. One more thing before we move on. There is a hint in the documentation about explicit layout and how it relates to the packing size. And I read this and I got confused. I'm not a native speaker, so I thought, OK, maybe it's just me. But I thought this could be read as, in certain cases, the offsets are not honored. That didn't sound right, though. So what did I do? I just tried it. So again, a simple example here. I got a byte, an int, and a long, explicit layout. The offsets are picked so that there is no overlap and no gaps. And in one case, I don't specify anything, so whatever the platform default is, I'll get. And in the other case, I say 1, so byte aligned. And so the good news is no, so the offsets are actually honored. So you say you want it at 0, 1, and 5, this is what you get. But there is a difference. The size here, it's not 13. It's not what I need, it's 16. So for the overall size of the struct, the runtime still looks at it and says, no, we got a long in here. So normally I would align this, and then this would go from offset 8 to 15, giving you a total size of 16. So it adds 3 bytes of padding at the end. Now, if all you want to do is pass around a single struct like that, it probably doesn't matter because the offsets are correct. And if your callee reads past the last field, then that's arguably a bug in the callee. But what if you have an array of these? Or what if this array is a member of this struct is a member of another struct and there's something after it? Then it might become all very important that it's actually the 13 bytes, or actually the 16, one of them, whatever is the correct one for your use case. But in those cases, you have to worry about this. So the offsets are always honored, but the overall size of the struct may differ depending on the exact layout and how the packing size is specified. OK, this was all very boring. What do I need this for? This is what I need this for, p-invoke. This is where it gets interesting. And p-invoke is a bit of a unfortunate naming. As far as I understand it, it goes back to the very, very early days of .NET. I don't know, who's been around for .NET 1.0, Anyone? Okay, a few. So you remember a lot of stuff that you wanted wasn't there. So, stuff that you need for your application, and by no means a very complicated thing, was not there yet in the BCL. But of course, it was there in Win32. So you need a way to invoke Win32, and I think this is basically where the naming comes from, because what it does, it's your gateway into native code. So it's like the JNI, the Java Native Interface in the Java world or JVM world. This lets you interact with anything that has a C-style ABI, application binary interface. That can be Win32, but it can be anything else. And of course, also the platform and what that is has changed. It used to be Windows, but now we can also have macOS or Linux. And as a little bit of a detour/warm-up exercise, let's quickly fill this gap about, what if I need memory that can't be on the stack because of lifetime or of size issues? So I can just go to the native unmanaged heap and say I want some memory. And one way to do this is there is this native memory class, and it has an alloc and a free method, and they just wrap the C standard library malloc and free functions. Very simple. So I say alloc, I say how many bytes I want. I get a pointer back for an allocation of at least that size, and when I'm done with it, I say free, and it goes away. Only problem is this is only available in .NET 6 and later. So what if you're still on .NET Framework? Well, not to worry, the operating system can do this too. You just ask Windows itself, I need some memory. It's a little bit more involved because a process in Windows can have more than one heap. Obviously, it has to have at least one heap, but you can have additional ones. As far as I know, it's an advanced scenario you probably won't actually hit. But because of this, the first thing I need to do, I need to say get process heap to get a handle to the default heap. And once I have that, very similarly, I can say heap alloc. There's the heap. There's some flags. I have some control about how allocations and deallocations are performed exactly. We're going to ignore this for this talk. And then the size again, how many bytes I want at least. And similarly, you can free this. Now, this looks a bit strange, right? This is weird C# because it's not. So this is strange from the C header files or from the Windows SDK. So if I just copy and paste this into my C# file, I get errors. How do I actually use this? Well, pinvoke /DLL imports. So what I can do on the managed side, I can say I have these static extern methods. So extern just means, OK, I have a function that is not implemented in this assembly, that's implemented somewhere else. In this case, I'm slapping on a DLL import attribute saying, well, this somewhere else is a native DLL with this name. So please load this, and it's going to have a get process heap function, and it's going to have a heap allocation and heap free function, and these are the signatures. That's pretty much it. I mean, yeah, we have pointers, so we can avoid pointer back from heap alloc, and we have to put it back into heap free, obviously. But that's the basic idea, and then calling this is no different than any other method too in .NET. So from the caller side, other than pointers being involved, it's just regular stuff. But how do I get from one to the other? And I guess it's a bit of a good news, bad news thing. So the bad news is you have to deal with header files. They have all the details in there. The good news part is you don't have to become a C programmer, but you have to understand enough to make sense of these header files, and they can get a bit involved at times. You also have to understand the value ranges of data types in C/C++, because your ints, your longs, oftentimes they have the same value ranges both in the managed and the unmanaged side, but it's not always the case. So you want to understand those, and more specifically for Win32, there's documentation about common types like handle, bool, all sorts of string types. That's a piece of documentation you want to reference. But you might ask, OK, but we should be able to generate this, right? I mean, it's code. It's C code. We can parse this. We can make sense of it. And the answer is somewhat. So for Win32 specifically, there is this C# Win32 project that does generate DLL imports and structs based on whatever it is you want to call. But this doesn't actually go to the header files. There is a dedicated metadata database that this is generated from. But still, if you're on, well, again, .NET 6 and later, and this is what you want, then this helps. There's also the Swig, I don't know how that is pronounced. But there's a project that actually does what I just described, that says, okay, it's a header file, and it supports a host of languages, including C#, and I say, okay, based on this and this header file, please generate me my imports. So I haven't tried either. So if you do, I would be very interested in hear about your experience. But I know about this caveat. So do not expect this to always work. It cannot. And I have this little quote from Brad Abrams. So the ones who've been there for .NET 10.11, they might remember him. So he blogged about this back in 2004, because people were asking, why can't you just generate it? And the problem is ambiguity. Now, this might change with AI. Maybe AI can then help and figure out the semantics of the parameters. But without that, the problem he outlines here is, say you're on the native side, you got a char pointer. Okay. What do you map this as? You can map this as a string, or a string builder, or fchar, or a char array, or an outref. He didn't even list those one. The point is you have multiple options. Some are clearly wrong for use cases, others are viable. Which one the best one is, you have to figure out based on the semantics and the use case, which a tool obviously will not know. So you can experiment with the tooling, but expect that you will have to do some manual overhaul with whatever that spits out. Now, calling conventions. That's another fun thing similar to memory layout that you could ignore until now. So how calls actually work, so this is part of this application binary interface. Doesn't matter, you got your C# code, it's compiled to IL, and you don't care about the rest. It just works. But now we call native code. So what this entails is just a few examples. It's a bit more involved. But so how are arguments actually passed to a callee? Do they go on the registers? Do they go on the stack? Combination of both. Similarly, then how does a return value make it back to the caller? It has to be passed somehow. And for anything we're putting on the stack, particularly arguments, right, somebody has to clean them up. They have to be popped by somebody. Well, this might be the caller or the callee. And the calling convention specifies all of this. And so DLL import actually has a whole bunch of more properties you can set to tell exactly how the imports are supposed to work. Calling convention is one of them. So if you have to specify it, the DLL import is a way to do that. The good news is, I think for the most common platforms I think you'll encounter, this is not going to be an issue. So Windows, 64-bit, Intel, there's basically one standard calling convention. Well, there's one standard calling convention, but there's also an extension to the standard, which is the vector calls. They use SIMD registers in addition to regular registers and stack. But they're also not supported by .NET. So if you want to do a vector call, well, you can't. You have to have a native wrapper for that in the first place and turn it to a standard call, basically. macOS on Apple Silicon on ARM64, there's literally only one convention. It's based on the standard for ARM64, and similarly Linux x64, 64-bit Intel, there's one convention. But if you still need to support 32-bit Intel Windows or anything I haven't listed, make sure that you understand if there is multiple conventions. If there's only one, then it'll use the one convention. But if there's multiple, which ones you need to use and when. But again, it probably should not affect you most of the time, so I'm not going into detail here. Lifetime. So at some point, we have some unmanaged resource. In my example now, it's going to be a SQLite database, for example. And when I'm done with this, I need to clean this up somehow. So how do I do this? So the sample here is fairly simple. What I want to end up with, I want to have a database class, and I new this up with the database/file name of that SQLite database. And then I want to be able to just execute scripts, arbitrary SQLite scripts. Of course, it's of limited use, but this fits in the slides. And then I have a script that just creates a table, just to insert, just to demo this on slides. So when I finally done and I run this, then when I open the database, I will have this table with 2 columns and 2 rows. So now you might say, yeah, but there's an ADO.NET provider, right? Why would you want to mess around with native code here? And by the way, there's also an EF provider based on the ADO.NET provider that you can use, so you didn't have to do anything here. So a little bit of context. I was on a project where we wanted an embedded database, and what mattered was speed. So industrial computers, in case you have never looked into that. The cheapest one are already extremely expensive and very slow. And we needed to be able to read and write entire rows mostly as quickly as possible, only very simple filtering. Don't even remember if we identified any joins we needed to do. So this is why we said, OK, we're going to use the library directly. And so for the limited example for this talk, what we need is there's a delegate callback. We'll come back to this, but 3 functions: open, close, and exec. So we can open database, we can execute scripts, we can close it. And a few things about the DLL imports. So you see entry point here. So before I did not specify this because I guess I liked the actual function name, so I had them match, but they don't have to. So if I want my extern function, the DLL import, to have a different method name than the original function, I can pick whatever I want, and then in the DLL import, I say entry point and give it the actual name of the native function. Another thing, marshal as. And we could probably do an entire talk just about marshalling. So it's basically changing data formats on call and return. In this case, for example, strings in .NET, they're UTF-16, and they're not null terminated. But SQLite expects UTF-8 null terminated. So I can do the conversion myself, and maybe if it's strings I use over and over again, that might make sense to do it manually and buffer it. But the easiest thing I can do, I can just say, hey, this file name, convert this before you pass it into native code. And then I have the safe database handle. So for that, I have an out safe database handle instead of an actual pointer. What's that about? So safe handles, they help us manage lifetime. So what's interesting, if you go to the documentation, it will tell you that a safe handle represents a wrapper class for operating system handles. And while true, not exclusively. So a handle that is an integer of the size of your platform, so 4 bytes on 32-bit and 8 bytes on 64, so you can't just cram a pointer in there. Safe handle doesn't care, works just fine. So this is what we're going to do. But we get another interesting benefit, and that is reference counting. So obviously, as you make your calls, you don't want this unmanaged resource to be freed before your last call returns. I'm not talking about callbacks yet, because that makes it more complicated. It's synchronous calls, right? You want to make sure that you don't free your native unmanaged resource until the last call comes in, and the runtime does reference counting. Every time you make a call into this native library, with this safe handle, it increments a counter, and when it comes back, it decrements, and if there now comes a dispose call or finalize call, it will not actually do this until reference count is down to 0. It's a very neat feature. And I mean, maybe you can guess this, but it's also thread safe. They are very, very straightforward to implement. So there's a base class safe handle. You just inherit from that. Then you have to override is invalid. They specified it like this. So this compares the handle to a known invalid handle or handles, and then gives it back true or false. We have to have a constructor, obviously, so we have a default constructor, and we have to call the base constructor that we pass in an invalid handle, in pointer 0, and true. True meaning this safe handle instance owns this unmanaged resource, whatever that is. And it's interesting, yes, you can pass in false, it's a bool, but documentation says don't do that. So I don't know why this is an option. So it is your invalid handle and true, end of story. And then you also have to override release handle that releases whatever the resource is. So it's a SQLite database. We just say close, and then we just return a bool if it worked or not. That's it. And then based with this, we can then create our database class that will do what I showed you earlier, where I want to end up. And for wrappers like this, you might get away with saying, OK, it's sealed. So certain problems you don't have because of this, and we implement IDisposable. We have a read-only safe database handle in there. And then in the constructor, we take the file name, we call open. Of course, we pass on the file name, but also pass out database handle. So, I mean, what SQLite gives me back is a pointer basically pointing at a data structure describing or somehow identifying my database, but I'm going to wrap this in a handle. Now, of course, check if it worked, throw exception. Obviously, if this were real code, you use a more meaningful exception type, and no finalizer. This doesn't need a finalizer because the safe handle has a finalizer. And you shouldn't rely on this anyway, but it's good to have. There's a chance it will get invoked. So you have that already for free, because using safe handles. Similarly, in the execute, so we call SQLite execute, we pass in that safe handle and the script, and optionally the callback. We don't need a dispose check, because the safe handle has a dispose check. So if the safe handle is already disposed, you will get your object dispose exception as you'd expect, because the safe handle does it for you. Less code on your side, that's great. And then, of course, the dispose also is very simple. You just have to check that the safe handle is not invalid, so that's valid. And then you just dispose it. Done. That's our wrapper. This brings me to callbacks. So I said ignore it first. Now we're getting back to this. So you have this delegate here, callback. It takes a void pointer, columns, and two pointers to bytes. So what this allows me to do if I use it, it allows me to get a callback for every row of every result set of my script, and then do something with that information. So the first parameter, void pointer we're ignoring, I can basically give a SQLite a void pointer that it gives back to me. But we're not using this in this demo. On that, I get the number of columns for this row, and then I get two pointers to pointers. It's basically an array of strings. So again, an array of strings of the values and the column names. And this is also like the examples I had with how do you get to the DLL imports in general, right? So you go to the actual header files, look at the declaration, map this to native, to managed. It's the same basic idea. Then just to recap, that's the execute you already had. So we can then call this with a callback, like so, for example. So again, the void pointer at the beginning, we don't care. We just say underscore. So let's just try iterate through all the columns, and for each one, get the name and the value, convert it back from UTF-8. In this case, I'm doing this explicitly, and throw in a new line when appropriate. And it's just say result OK or error, because this result goes back into native code. So I should not throw an exception here. Native code does not know what to do with that. And that works. That's great. But, so what's a delegate? Well, it's a reference type. It's an object. It's somewhere on the heap. It's subject to garbage collection. So into demo then, what happens when we are not careful with this? I created what I think is the world's most pointless C library. It's this here. So what this does is we have a global variable called callback pointer. So it's a pointer to a function pointer that is parameterless and void returning. So it just does something. And then I have set callback and call me maybe. You'll see how where the maybe comes in. But yeah, this has something to do with the lifetime. So, and then we call set callback. We get the function pointer passed in. We just remember this, and then call me maybe. We try to invoke this function pointer, and that better be valid, because otherwise. So on the native side here, I omitted now the DLL imports. They're pretty straightforward and boring. But I have a static setup and trigger native callback that has a nested function, say hello. It just writes hello.net to the console, pretty straightforward. And I say set callback, say hello. So I'm passing a callback to native code. So this creates a delegate implicitly, has to. And then I say call me maybe. So when I'm saying native code, OK, try to invoke whatever I give you. And then I call this setup and trigger native callback, and that works just fine. OK. But now I want you to remember the state that I set up. And it is convoluted like this because when we're done, when we're here, the delegate that I used to call set callback, it's out of scope. Nobody's referenced it anymore. It can't get collected now. So let's do that. Let's say gc collect and also run the finalizers, or well, they're going to run, but let's wait for the finalizers. And then try again to call me maybe. and catch if there's an exception. Now, you would probably expect that there's an exception because I already said, there's a delegate, it's out of scope, it's not referenced by anything, we should get collected. So it should be an exception. Except for not what you're thinking of. Your process actually dies. So it's an exception of some sort, but nothing you can catch. Because now we have to think about now what's happening here. So you can't pass a delegate directly to native code in the first place. Can't be done. It's an object on the heap. So what the runtime does, it actually creates a thunk. It creates a little piece of code that is callable from native code and that then invokes your delegate. But you have to have this little piece in between the two. But this is gone now. The delegate is gone, and when the delegate is gone, also my thunk is gone. So basically what's happening here now, the native code is now trying to dereference a function pointer, not pointing at anything valid, it's dangling. And the runtime now says, okay, this is a fault in native code, we're done. But it gets better. So let's do this again. So we say set up and trigger native callback, we're going back to the state, and now we collect, but don't wait for the finalizer. So your mileage may vary if you try this yourself. I'm trying to get a race condition here. So I'm trying to keep going before the finalizers do their thing. And if I pull this off, now I have a null ref exception. So the point here, the exact behavior will depend on the exact timing. Now, I probably need to dig in the code at some point, but I think the only plausible explanation here is if I do this, the finalizer is actually the one that cleans up the thunk. The finalizer is not run, the thunk is still there. And it runs, and then it tries to access that delegate, but the delegate is gone. So, long story short, you want to get the lifetime of delegates you hand out to native code right. Otherwise, you have to deal with this. Which kind of begs the question, is there a better way, a more straightforward, easier way? And if you're on .NET 5 or higher, then yes. If you are okay with your callback method being static and being only for callbacks for native code. So what I can do this, I can change my third parameter to this. And I don't know how you feel about seeing this. When I first saw this, like, what the hell is this? So it's a delegate pointer, but also looks like there's generics in there. No, this is an actual function pointer in .NET, say in C#, despite the funky syntax here. So delegate start, this means it's a function pointer. Then I specify the calling convention. I have to do this here because it has a default, but the default is managed, actually. That's not useful for pinvoke. And then what looks like generics, you have to read this like your funcs. So the last one, that is the type of your return value, and the other, that is the types of your parameters. Okay. So I can do this, and then, of course, my execute changes accordingly, nothing else. And then I can rewrite how I use this like this. So I grayed out the body because that is the same. I'm still doing my form, I try, none of this has changed. But now I'm saying, okay, I want to have a method that is unmanaged callers only, and this is enforced. If I now try to call print roll from your regular C# code, that's a compile time error. Also, I have to specify the calling convention here, how this is supposed to be called. And then now I have the option to say address of print row. I'm actually getting a pointer. So yeah, it has fancy syntax for how you specify the function pointer types. And you have to have separate entry points now in addition that are not callable from managed code, but this is a viable alternative. And then you definitely don't have this delegate problem because there's no delegates anymore. All right, almost done. So what you should check out next, and basically I say further resources, but it's all Microsoft Docs actually, and they're really well written. And I really mean this, no sarcasm in there. I use it a lot to prepare this talk too. I think I had one or two links on earlier slides as well. So one is the unsafe code pointer type function types documentation. So that describes unsafe and all the things that you can do that I showed you. Pointers and address of and stack alloc and fixed buffers and all this good stuff. I also want to point out the actual specification. That is very verbose, and it's written in a very almost academic style because it's an actual standards document. But to really understand maybe parts of how unsafe work, or if you just out of curiosity want to drill deeper into a particular area of unsafe, this is a great resource. And then finally, there's a native interoperability guide. This is not just a page. This has pages and pages on how to call native code, how to call COM objects, marshalling. So probably not necessarily for trivial examples, but at some point you want to look at that. Now, for the most part, I kind of assume you're on .NET 6 at least, but a few words if you're just on .NET Framework. So actually, who is still doing .NET Framework development here? Yeah, a few. So it's not much here that I really want to point out that's important. One is, I already showed you heap alloc and heap free from Win32. Please do use those. Do not use marshal.alloc_hglobal and marshal.free_hglobal. They work, but they actually map to legacy Win32 APIs. And when I say Win32, actually those functions that they map to have been run since Windows 16. And the documentation also discourages you from using them. And lastly, we're not going to go into what that means. I mean, if you know what this means, you're probably cringing already. If not, read up on your own time. The safe handles in .NET Framework are CERs. So there's limits to what you're allowed to do in those. And so you need to be aware of those rules and follow them. With that said, thank you. Any questions? Okay. Yes.
So,
oh, microphone.
All right. Yeah. Thank you very much. So the difference between managed code and unmanaged code in the intermediate language, is there any? Will the unmanaged or the unsafe code be directly compiled into native code? No. Or is there an intermediate step?
No, it has nothing to do with how compilation works.
Okay.
So unsafe codes just means, in terms of how the runtime looks at it, it's unverifiable. Verification in the sense where when you don't have unsafe code, the compiler checks all sorts of things in terms of memory and type safety. And those are then guaranteed. Certain things just can't happen. You can't have a type mismatch. You can't read past array boundaries, these kind of things. When you say unsafe, basically additional features even in IL become available to you. That means that the result is not verifiable anymore, but the compilation is exactly the same. All the unsafe code is compiled to IL and then to native code at runtime, just as the rest too, no difference.
Okay, so the IL code for a basic for loop would be the same for unsafe and safe code.
Yeah.
All right, thanks.
So the difference in IL are basically now the same as in C#. Now in the IL, I can have a pointer type, right? So because IL supports all this, I don't know who knows a bit or has dabbled in C++ CLI. So there's a version of a dialect of C++ that supports both native and managed code, where you can miss and match. But even in this case, anything where you say this is managed code, that's then typically also unsafe, that's compiled all into IL. And only the parts where you say this is native code is compiled to native code. So it does not make a difference. It makes a difference in terms of what IL/runtime features are available to you. That's it. Any more questions? Well then, thank you so much. And I know it's a bit of information overload, a lot to take in 60 minutes. I'm still around at the conference. The slide deck is on GitHub. You can download it there. Also, you can hit me up on LinkedIn or Mastodon. So again, thanks for attending today. Have a good day. Have a great NDC Porto. So, what I'm even in time.